Welcome back to Train Signal's VMware vSphere 5 training. You're watching vSphere Virtual Networking lesson. Alright, so in this lesson we're going to cover the virtual connectivity to the physical network, the rest of the physical servers, appliances, storage that are on our physical network. It's going to be a very cool lesson. We're going to start off by talking about virtual networking, what it is, and some of the similarities between virtual networking and physical networking. We're going to discuss the differences between physical networking and physical switches and virtual switches. We're going to talk about some of the virtual standard switches, which is what VSS stands for. What are they exactly and how they differ. We're going to talk about where you can take a look at your network adapters in your vSphere infrastructure. We're going to talk about the different types of virtual standard switches that you have access to. So for example, if you wanted to create sort of like an isolated virtual switch where the virtual machines that are on this virtual switch can communicate with one another, but they can't communicate with the rest of the devices on the network, on the physical network, or even other virtual machines, you can isolate them. So we're going to take a look at, how many types of virtual switch types are there. We're going to talk about the different virtual switch ports. So there's different types of virtual switch ports. For example, you have virtual machine switch ports. That's typically for virtual machine traffic. You have the VM kernel, which you can pass stuff like the management network. You can stuff like the IP storage, vMotion, etc. We're going to discuss MAC address changes. What does it mean? How can you lock down MAC address changes so nobody can sort of try to capture that MAC address, mask itself with that particular MAC address, and try maybe to do sort of like forged transmits where it seems like it's coming from a MAC address where it's not coming from that particular one. We're going to discuss VLANs. What are they? How can they be used? And why can they be used? And how to connect your physical or your VLANs from the physical switches into your VLANs, or extend that connectivity into the virtual switches. This is going to be a very cool lesson, so go ahead and brace yourselves. Alright, let's go ahead and get started. So what is virtual networking and why do we need it? Virtual networking, in its purest form, is simply the building block or the cornerstone of an IP network that's built primarily for virtual machines. Now this virtual network, virtual IP network that we're building is going to help connect those virtual machines to the physical network. So the same way physical machines and physical devices require a physical network in order for them to communicate with one another, virtual machines also require a virtual network in order for virtual machines to communicate with one another, but also to integrate this virtual environment with the physical environment and allow for a seamless connectivity of virtual machines or virtual devices with physical machines and physical devices. Now I've always said that whenever you think about virtual machines, you got to think they have the same components, the same requirements as physical machines. So a physical machine requires a physical NIC card, a virtual machine is going to require a virtual NIC card. If a physical machine requires a switch, a physical switch to connect to in order to get access and have communication with other devices, then a virtual machine is going to require a virtual switch to connect to and get access to other virtual machines and other devices. A virtual environment mimics a physical environment, except instead of having physical hardware, you have virtual hardware. So let's bring up a whiteboard here and illustrate a little more how this works. In the traditional sense of networking, each device required a NIC. This NIC allowed the device, whether it is a server, an appliance, a router, a printer, whatever it is, it allowed this device to communicate with the rest of the devices and appliances that are on the network. Now, with the introduction of virtualization and VMware, you have one big host, which is the physical device, and then you have several virtual machines running on this physical host. Now, in the traditional sense, you would need a NIC card for every virtual machine to allow connectivity to the rest of the network. So what do? It doesn't make sense to add 20 or 30 NIC cards in a host to give connectivity to all these virtual machines. And this is where the concept of a virtual switch comes into play. A virtual switch mimics a physical switch, except it's software based, as you may know, and it will have ports on it. And these ports can be added or deleted. You can have 24 ports, 51 ports, 52 ports on a virtual switch. Now the idea here is to connect one or more NIC cards, physical NIC cards, to this virtual switch. So this virtual switch is serviced by one or more physical NIC cards. At this point, what we do is we connect these virtual machines to the different ports that are available on this virtual switch, and as such, we give them connectivity to the outside world or to the network. Now, this is just a very basic idea that gets more complex and it's more interesting, and we're going to get into the different scenarios and different types of scenarios that we can tackle here, but I just wanted to give you a quick breakdown of how things work in order for us to be able to make more sense out of the next slide that I'm going to bring up here. Alright, so let's move on with our presentation here. ESX Server is going to perform a discovery of all the available physical NIC cards that are installed on this host. And as you can see in this figure, and we're going to log into the VI client in just a second here and show you how this looks like in the live server. But as you can see in this figure, under the configuration tab, if you click on network adapters, you're going to see a list of all the physical adapters that are available, and if they have an IP address that's assigned to them, that's going to be displayed too. If they're part of a trunk, you're going to see a subset of IP addresses that this NIC card can see or has access to. Let me show you where that is. So if you've logged on through your vSphere client and you click on Hosts and Clusters, and you select one of your virtual or one of your ESXi hosts, and you click on the Configuration tab here, if you click on Network Adapters, you'll get a list of the different network adapters that you have access to in this environment. So you'll see that for me, I have two physical NICs. They're 10 gig physical NICs. From a duplex perspective, they're set to negotiate, so they can auto-negotiate the speed. Now, obviously, this is 10 gig, so it's not like when we were using 100 meg, where there was a duplexing mismatch possible because you had half and full. With 10 gig, it's going to be full, but you still have the idea here of the duplexing speed. You also have what virtual switch are they currently connected to, if they're connected to any virtual switch. You have the MAC address that is also displayed, and if you scroll a little bit over to the right here, you'll also see any particular observed IP range. So if there's any particular VLANs that this NIC can see, these VLANs would also be listed here. So if they're configured in a port trunk and you have access to multiple VLANs, they would all be configured here. Now, this is helpful and useful just in case you're going through a troubleshooting mechanism and you're trying to find out why some virtual machines aren't able to get connectivity to a particular VLAN. You can come in here and see if those VLANs are being observed by this the physical NIC that you have as an uplink for that particular virtual switch. Now, you can also see if Wake on LAN is enabled or not. In my particular case, it is. So just a quick snapshot of what's going on from a physical NIC perspective. Let's go ahead and switch back to the presentation now and start talking about virtual switches. So virtual switches are logical objects that reside in the VM kernel of each ESX server host. What this basically means is that virtual switches are made up of software that live inside the VM kernel. Now, the same way a physical NIC that's connected to a physical switch has a unique MAC address that identifies it on the network, a virtual NIC connected to a virtual machine is also going to have a unique MAC address that identifies it on the network. Now, with virtual switches, you can also bound one or more physical network adapter cards to each one of these virtual switches. Virtual switches can also contain one or more connection types, otherwise known as port groups. Port groups or connection types define the type of communication expected through the virtual switch. We're going to get into this in more detail a little later on in a few slides down. Virtual switches also operate at layer 2 and can provide VLAN tagging, security, checksums, and segmentation of load units. Now let's take a look at some of the similarities that exist between physical switches and virtual switches. Virtual switches are similar to physical switches in that they both maintain MAC address tables, they both look up each frame's destination MAC upon arrival, they both forward frames to one or more ports, and they both avoid unnecessary deliveries. Now, some of the differences that exist between physical switches and virtual switches. Virtual switches cannot be connected to other virtual switches. whereas physical switches can be connected to other physical switches. Virtual switches do not require spanning tree protocol. They also prevent loops in the switching configuration by using virtual switch isolation. Forwarding table is unique to each virtual switch. Now there are three types of virtual switches that exist. There's the internal only virtual switch, which is sort of an isolated virtual switch. This virtual switch has no physical NIC bound to it, which means the virtual machines that are connected to this virtual switch have no way of communicating with the rest of the network. Now this would be ideal if you're trying to set up some kind of a test development where you wanted to isolate an application and you wanted to build an environment that mimics your existing environment, but you didn't want to have any kind of conflict via either by using the same names or by using the same IP addresses, or even if you're doing an Active Directory domain and you didn't want SID conflicts or having different domain controllers that are playing the same roles, you could create your entire environment inside or access through this virtual switch that's isolated from everything else. The only communication that happens with an internal only virtual switch is between virtual machines that are connected to this internal only virtual switch. Now the second type of virtual switch that exists is a single adapter virtual switch. This basically means that the virtual switch is bound to a single physical adapter, and this physical adapter is this virtual switch's way of communicating with the rest of the network. Now the third type is NIC teaming, whereby you bound two or more physical adapters to a virtual switch. This provides for load balancing and bandwidth aggregation for communication with resources on the physical network. Alright, so we're back in our ESXi environment, or in our vSphere environment. And let me show you, let's talk a little bit about virtual switches and try to demonstrate some of the things we've been talking about. So if you click on networking here, and by the way, you get to it the same way, right? So if you select one of your hosts in your cluster here, you click on configuration. This time we want to go to networking. This is where all of virtual networking is configured. The first thing that you'll notice I have is I have a single virtual switch that is configured with one uplink, and that has several port group types in it. Now, if you were comparing this to the physical environment, you can think of this as, well, there's an Ethernet cable plugged in to a particular port, and that port is servicing a server, a physical server, and then you have another port here plugged in and servicing something else, right? So with virtual switches, you have these virtual ports that you can create and have virtual machines attached to them. And the same way as with a physical switch, where you can have that port group do something different, with a virtual switch you can have it do something different as well. Now you'll notice I have management network down here, and that means that this is the virtual switch that provides connectivity to manage the host. This is how you connect to manage the host, and you connect to it on this particular IP address. Now, in the event that I should lose this physical NIC, I am losing access to managing this particular host. So how do I provide some sort of redundancy to get maybe a backdoor, a second entry into the host, so that I can manage it from another entity, right? So look, there's a couple different ways of doing this. If I wanted to add another uplink here, another physical NIC that would provide redundancy at the physical NIC level. So if I lose one, the other one continues to operate. Let's see if we can do that. If I click on properties here of the virtual switch and I go to network adapters, if I have an additional physical NIC to add to it, I can click on next, next again, finish. And we're going to click on close, and you see now this particular virtual switch is now being serviced by two physical NICs. So in the event that I should lose one of the physical NICs, the other one will automatically pick up, and it will continue to service this host, and I can continue to have access to it. However, at this point you're putting all of your eggs in one basket, right? So you're relying on the actual virtual switch never going down, and in essence that's true. But if you wanted to do this in a different way, we can click, just because I don't have a lot of NICs, let's go ahead and remove this particular NIC out of here. And you can see how easy it is for me to add and remove NIC cards. It's very easy. If I wanted to create a redundancy at the virtual switch level, what I can do is I can click on Add Networking here, and I'm going to select VM kernel. I'm going to click on Next. Then I'm going to select that particular physical NIC again. And let's say I'm going to call this management network 2. And you can, if there's any kind of VLAN, you can add that particular VLAN. We'll talk about VLANs here in just a second. But in order to turn this into a management network, as you might have figured, you're going to click on this checkbox. You click on Next. Now you have to IP it. So we're going to give it a particular IP on the network. So let's say, in my case, let's do 10.4.14.66. And let's do 255.255.255.0. And voila. So what you end up with in this case is now you have redundancy. If you completely lose this virtual switch, you can't connect on this IP address anymore, but you can connect to this particular server and manage it off of the second interface that we've created here, which is through 10.4.14.66. So this is how you can create redundancy for the management network itself. Let me go ahead and remove this particular virtual switch. Now, during the presentation, we were talking about how you create internal-only virtual switches so that you can add virtual machines to them, and those virtual machines can only communicate with each other, but they can't communicate with the rest of the devices on the network, and those devices can be physical or virtual. To do that, we're going to click on Add Network. We're going to select virtual machine because the purpose of this virtual switch, we're creating a port group. And what a port group is, in essence, is you're selecting, hey, I'm going to dedicate 5 or 10 ports that I can plug certain machines into them. So what we're doing here is we're saying the port group type is going to be virtual machine, so that virtual machine traffic can pass through. But I'm not going to select any kind of an uplink, so I'm going to uncheck the box here, and I'm going to name this one internal. Click on Next. We're going to click on Finish. And we've just created a virtual switch that is internal only. So any virtual machines that you add to this particular virtual switch have absolutely no connectivity to the rest of the world. So they can't even communicate with virtual machines that are on this other virtual switch. They can only communicate with virtual machines on their own virtual switch. That's again, for highly isolated, if you're doing test, development, whatever the case might be. Now, as we talked about from a service console perspective, adding multiple uplinks to a virtual switch provides redundancy in that, if one physical NIC fails, the other one can pick up. But once you have a lot of virtual machines on a particular virtual switch, you can add other uplinks here so that these virtual machines can choose one uplink or the other to send their traffic through. So thereby you're load balancing the traffic that's going out of your virtual switch and out of your virtual machines. So you can very easily add another uplink over here. Now let's talk about different types of port groups that we can create. So I already mentioned to you that you can create either virtual machine port group, which means you're going to be passing virtual machine traffic. And we spoke about VM kernel. Now VM kernel, if you select this particular type, every time you do VM kernel, then an IP address is required. And the function of the VM kernel port group is defined in the next screen here after you select the uplink, so you have to give it a physical NIC. You have 3 types of functions for VM kernel that you can choose. If you select the first option, you're enabling vMotion. Now pay attention to vMotion. If you select vMotion, the label of your network here is very important, and it's case sensitive. Whatever you label your vMotion network, it has to be the same on all the other ESXi hosts, otherwise the vMotion process will not complete successfully. So make sure whatever you put for vMotion, you're copying across the other ESXi hosts, and it's case sensitive. If you select fault tolerance, then you're enabling your vSphere environment so you can protect the virtual machines with fault tolerance. So you can right click a particular virtual machine, drag down, and I'll show you in a second, enable fault tolerance. Now for fault tolerance to work, this would have to be enabled on one or more ESXi hosts. And again, the last one is for management network. So if you wanted to add another port group to a virtual switch, you can do so as well by just adding that particular checkbox here. Now the other thing that I wanted to mention is that you can have multiple port groups on the same virtual switch. So in this case, if we examine the properties of this particular virtual switch, you'll see that I have several types of port groups, right? So I have a port group for virtual machine network, and I also have a port group for the management network. Now if I click on the management network here, it gives you a snapshot of what's going on, what is the IP address that is dedicated to it, so on and so forth, so you can scroll down a little bit. If you wanted to modify certain aspects of it, you can just click on Edit, and then you can come in here under IP settings. You can change the IP, etc., etc., change the default gateway. You can also set it to obtain address automatically. Obviously, best practice dictates that you don't do that. But you can modify the settings of this particular port group by doing so. So you can always mix and match port groups. You can have a virtual machine network port group, and you can have several. So I can click on Add and add another virtual machine port group into this virtual switch. Maybe I'm adding another VLAN. Maybe I just want to add IP storage. Any number of reasons. vMotion, you can add it on this particular virtual network as well. So this is virtual switching in a nutshell here on how to present these virtual switches in a redundant way and how to use them properly. All right, so what I want to do now is switch back to our presentation. All right, so the definition of the virtual machine port group is that members of the port group are going to get access to the rest of the physical network via a switch-to-switch connection. So the virtual switch is going to make a connection with the physical switch and pass the traffic from the virtual machines out to the rest of the devices on the network. The physical switch is going to receive the traffic from all the physical devices, pass it to the virtual switch, and pass the traffic that's destined to the specific virtual machines. This is really cool stuff if you think about it. I can't help but remembering the movie The Matrix and the link between the virtual world and the physical world. And you can see the relevance of the communication here. You are mimicking physical devices in virtual, and you're spreading them in virtual. I mean, you're able to have 20, 30 virtual machines connecting to a virtual switch that's then connecting to a physical switch, which spreads out to all the physical devices. It's pretty cool. Now this next slide is really pretty cool as well. It shows you the power of virtualization here. So take a look at this. This green circle, think of this green circle as communication between physical and virtual machines. This is one of the ways that you can configure your virtual switches, is to pass the communication between virtual machines, physical devices, etc., etc. But you can also do, and we talked about this, you can also, with a few configuration settings, create an isolated environment from the physical network or from the rest of the virtual machines that are in the production network. Just imagine how much time this is saving you and how much time this would have taken you to set up an isolation environment if you needed to for a test and development with physical devices. I guarantee you it would have taken hours, if not days. Now you can do it in a matter of, 20, 30 minutes. You have everything up and running. You're passing it on to the developers. So you're saving a lot of time. You're increasing productivity. That's the power of virtualization. Alright, so now let's shift our attention a little bit and talk about VLANs. So what's a VLAN? In a very brief definition, a VLAN is a logical configuration of a network on switch ports to segment IP traffic. What this basically means is, without VLANs, what ends up happening is all the physical ports on a physical switch end up being part of the same subnet or part of the same network. So without VLANs, there's no way to carve up those ports to say, I want this specific port to connect to this network while that specific port to connect to that network. All the ports are part of the same network. The power of VLAN is it gives you the opportunity to have multiple networks present on the same physical switch based on ports. You can group ports together, say ports 1 through 5 belong to VLAN 101, which is my server VLAN. Ports 6 through 10 belong to VLAN 102, which is my printer VLAN, for example. So some of the many advantages of using a VLAN is that it allows you to save on hardware. Without VLANs, then every time you wanted to add connectivity to a particular network or subnet, you would have to have another switch. By using VLANs, now you can have one switch and then configure the networks or your subnets on a port-by-port basis. This saves you a lot of money and a lot of time as well. VLANs also allow IP subnets to extend beyond the distance limitations of the physical medium. So typically what happens is a VLAN is present in the configuration of one physical switch, but the VLAN on switch A, for example, doesn't know about VLANs that are available on switch B, and thereby cannot pass traffic to those VLANs. Now this is where advanced VLAN configurations come into place, where you can have certain ports on physical switches that are considered trunk ports. And a trunk port, in essence, is a port that has knowledge of other VLANs that exist on other switches. Now, by having this knowledge, by having those trunk ports, now you've made the VLANs that are available on the other switches accessible to this VLAN. Now it can route traffic to it, it can pass communication across it. Now, I'm sure a lot of you are probably asking, why are we talking about VLANs and such advanced networking concepts when we are trying to learn about virtualization? Well, the fact of the matter is, virtual networking is an imperative part of virtualization. And I'm going to give you an example here. Why are VLANs important to virtual networking and virtual switches in particular? Well, without VLAN tagging, without support for VLAN tagging inside virtual switches, you're going to end up having to dedicate a physical NIC to every network or subnet that you're trying to give your virtual machines connectivity to. So if your environment looks like a lot of the ones that I've seen, whereby you have your servers in VLAN 101, for example, and then you have your terminal servers in VLAN 102, and your file and print servers in VLAN 103, and your Novell servers in VLAN 104 or 105. You have all these VLANs. Every network environment typically has, tens or hundreds of VLANs. Now, if you wanted to give virtual machines access to these VLANs, you'd have to dedicate a virtual switch with a physical NIC to each one of those networks. But by giving virtual switches support for 802.1q, otherwise known as VLAN tagging, now the virtual switch that has one dedicated physical NIC to it can have visibility and connectivity to multiple VLANs. So you have one virtual switch supported by one physical NIC. This physical NIC is connected to a port on a physical switch. Now the physical switch port is configured so it can see multiple VLANs. You can pass this visibility on to the virtual switch, which passes it on to virtual machines. Now you can have virtual machines configured to connect to VLAN 101, virtual machines configured to connect to VLAN 102, 103, and so on. However, to illustrate how you can configure VLAN tagging, we're going to show you how to do that from within the vSphere client. Alright, so we're back in our virtual center server here. Now, to illustrate the next example, let's go ahead and click on Properties, go to Network Adapters, and add the second adapter that we have here. Click on Next, Next, and Finish. And let's go back into ports, and let's talk about VLAN tagging a little bit. So if you wanted to create multiple VLANs and give your users or your VMs access to these multiple VLANs on your virtual switch, it's very, very easy to do. So let's say you wanted to add a VLAN to this particular virtual or this particular port group. You can click on it, click on Edit, and down here where it says VLAN ID, if you have 802.1q enabled, then you would come here and you would match the VLAN ID here with whatever the VLAN ID is configured by your network administrator on the physical switches. So make sure they match. So for example, it could be 101 or it could be 114. Whatever the VLAN ID is, you can come in here and set that. And then if we click on OK, and if we click on Close, you'll see that now I've created a VLAN ID. Now, if you wanted to add another VLAN to this particular virtual switch, what you can do is you click on Properties. We're going to click on Add, click on Virtual Machines. That's because the port group that you're creating is virtual machine traffic. And you can come in here and say, well, we want to do 102 this time. And you can give it a different label if you wanted to. And then bada bing, bada boom, you are done. So when you click on Close, this is what it looks like. So now you have configured VLAN 101 and VLAN 102 on this particular virtual switch, going through the same uplinks. So again, you don't need a dedicated physical NIC for every subnet or every VLAN that you have in the environment. You can enable port trunking and VLAN tagging so that you're using the same physical NICs, but you're able to pass traffic to multiple VLANs. And this is how you can come in and configure your virtual switches to accept VLAN tagging. Alright, now that being said, let's go into the properties of this virtual switch and let's examine what we can do with this particular virtual switch. Alright, so let's go ahead and go into the properties here, and let's start off in the General tab. Now, think about this. The first thing that you have access to is what is the number of virtual ports that you want to make available on this virtual switch. Now, by default, you have 120. Now, you can increase that, and you can go all the way up to 4,088 ports on a virtual switch. Have you ever heard of that number on a physical switch? Is it that easy to add more ports on a physical switch? Just imagine if you wanted to add more ports on a physical switch, you'd have to go out and buy another physical switch. Well, with a virtual switch, I can come in here. How many ports do you want? You want 24? You want 56? 120? What about 4088? Does that satisfy your need? So it's very easy to add more virtual ports to a virtual switch. However, I'm going to keep it at the default number here of 120. You can also control the MTU, the maximum transmission unit, that's coming out of this particular virtual switch. So by default, it's set to 1500. You can scale it up or down based on, from a performance perspective, if there's any need to do so. I wouldn't touch this particular value unless there is some kind of a troubleshooting, or if you found out or if you've investigated a performance boost out of doing so. Otherwise, I wouldn't change that. Now let's move on to the security tab. The security tab is interesting. So let's start off with promiscuous mode. Promiscuous mode by default is set to reject. Now what is promiscuous mode? Promiscuous mode, if you enable it, and your options are either reject or accept. If you set it to accept, then what you're doing is you're exposing all the packets that are coming into this virtual switch to all of the virtual machines on this virtual switch. So every virtual machine, technically, if there's a smart user there, can see all of the packets that are destined for any other virtual machine on this virtual switch. Now obviously this is a security issue. You don't want a virtual machine to see the packet of a different virtual machine on the same virtual switch. However, can you think of a scenario where you would want to put this to accept? Anyone? Well, so if you set intrusion detection systems, or if you're troubleshooting, or maybe a Wireshark or something like that, then you're absolutely correct. If you're going through a troubleshooting, or if you've installed some kind of an intrusion detection system on the network, then you want that intrusion detection system, you want Wireshark, you want your troubleshooting mechanisms to be able to capture all of the packets that are incoming to this virtual switch. So that's one of the only reasons why you would set promiscuous mode to accept. Otherwise, by default and for best practices, you set this to reject. Now, from a MAC address changes perspective and from a forged transmits perspective, by default they're set to accept, and you can set them to reject if you wanted to. And I'm going to bring up a slide in a second that will help me explain what these are and how they work. But basically, what you're doing with a MAC address changes is you're setting the MAC address that the guest operating system is transmitting, the MAC address of the guest operating system, and the MAC address that resides in the VMX file of the virtual machine. And VMX file, by the way, just as a refresher, is the configuration file of the VM. So whatever the VMX file is registering for this particular VM, and whatever the guest operating system is hard-coded to know from a MAC address perspective, they would have to match, otherwise the traffic isn't going to be allowed. Now it's the same thing, and this is for incoming traffic. MAC address changes is for incoming traffic. Forged transmit is for traffic that is being transmitted from the virtual machine, and it's the same kind of concept. The guest operating system hard-coded MAC address and the MAC address that is registered in the VMX have to match. Now, by default, the MAC address isn't hard-coded in the guest operating system, and I'm going to show you where in the operating system you can see that particular value where you can hard-code the MAC address. Now, keep in mind, when a virtual machine is jumping or being vMotioned from one ESX host to another ESX host, its MAC address will change. So be careful when selecting this particular setting. If you set it to reject, you might interfere with the vMotion process. So again, from a high security perspective, it should be set to reject, but again, be careful. If you set that to reject, you might interfere with the vMotion process on both of them as a result of that. Alright, so let me go ahead and switch back to the presentation here, because this will help you better understand the MAC address changes and the forged transmits. Alright, so what happens here is that the MAC address that's defined in the guest operating system, as you can see in our figure, it's a Windows operating system. When the MAC address in the guest operating system does not match the MAC address specified in the VMX file, and the VMX file is the virtual machine's configuration file. So basically, the address in the guest operating system and in the VMX configuration file need to match before traffic can be allowed to pass through. If they don't match, then traffic is rejected. Now, MAC address changes is, as you can see because we've underlined it, is for incoming traffic into a VM. Now for outgoing traffic from a VM, again, if the MAC address that's specified in the guest operating system does not match the MAC address specified in the VMX file, then the traffic is not going to pass through. Okay, so back in our vSphere client, let's keep going with the tabs of the properties of a virtual switch. If we click on traffic shaping now traffic shaping by default is set to disabled. And the reason it's set to disabled is NIC cards are relatively cheap these days. It's easier to add another NIC card into your blade or into your physical server than it is to try to do traffic shaping and quality of service in the form of QoS against the traffic that's coming into or out of the particular virtual switch. It's really not worth the management hassle of sitting here and tweaking the average bandwidth and the peak bandwidth and etc. to be able to squeeze that inch out of the bandwidth that you have. It's much easier to just add another physical NIC and call it a day. However, in the event that you do want to do some kind of traffic shaping, some kind of QoS on your virtual switch, you can come in here under traffic shaping. By default it's set to disable, but you can always enable it. And then you have several different options, several different policies by which you can tweak the bandwidth. So the average bandwidth is in kilobits per second. And so you can tweak the average bandwidth that's allowed into or out of this particular virtual switch so that you can configure it properly. You can configure the peak bandwidth. How much are you accepting from kilobits per second again as far as peak is concerned, and how are you configuring your burst size? What are you allowing from a burst size perspective? So again, these are policies that are available to you if you wanted to do traffic shaping against the virtual switch. I'm going to keep this at disabled. Now let's go ahead and move to NIC teaming. Now, NIC teaming provides a lot of benefits, right? So it provides load balancing, it provides redundancy. It's a great feature to have. As soon as you're adding two or more physical uplinks, physical NICs to a virtual switch, you have NIC teaming. And as a result, you have the option of tweaking some of the load balancing policies, some of the policies on how to handle this NIC team within your virtual switch. So from a load balancing policies perspective, you have several policies that you can choose from. The default one is route based on the originating virtual port ID. And what does that mean exactly? So every virtual machine is associated with a virtual port on the virtual switch. And every one of those ports has an ID. So for example, let's say you have your virtual center is a virtual machine. So let's say it's called vCenter 5. vCenter 5 might be connected to port 1 on the virtual switch. So what this is saying is I want you to route based on the originating port, a virtual port ID. So if virtual center 5 is transmitting from virtual port 1, then I want the incoming traffic to come back through virtual port 1. And the reason that's set up is because when you're transmitting via a port ID, the port ID is going to select one of the physical uplinks that are available, and it's going to transmit from that physical NIC. Now the idea is you want to receive the packet using that same physical NIC. So if it's possible, I want you to receive it using that same physical NIC. And so as a result, that's the first policy, and that's by default. Now, the second policy that you have here is route based on IP hash. Now, what that means is it's going to create a route or an IP hash based on the source and destination hashing, and it's going to route the traffic that way. The third option that you have here is route based on source MAC hash, and what that means is it's going to route based on the virtual machine's MAC hash, and it's going to determine which one of the physical uplinks it's going to use. Now, use explicit failover order. Now, if you select this, I want to shift your attention down here to this box. Now, down here in this box, you have two physical uplinks that are servicing this particular virtual switch. Now, each one of those physical NICs has an ID. So you'll see you have an ID 0 and ID 1. What happens here is it's going to route based on the lowest number of the lowest numerical value of the vmNIC. So in this case, it's going to route using vmNIC 0. It's always going to route all of the traffic from all the virtual machines on this virtual switch using this particular NIC. In the event that this particular NIC isn't there, it's not available, then it will start routing traffic using vmnic1. So in this case, what you're doing is you're explicitly telling it that I always want you to route the traffic using this physical NIC. However, in the event that this physical NIC isn't available, then you can go ahead and start routing the other way. Now, if you wanted to do it another way, maybe you wanted to route based on the first NIC, you can move it up or down and configure the order however way you want. However, the first NIC is the one that it's going to route the traffic through at all times. So what I want to do is I want to set this back to its default value, and let's focus on network failover detection. So you have two options from a network failover detection. What that means is exactly what it means, right? Exactly what the label means. How is it going to detect a network failure so that it can initiate a failover? So it's going to, if you select linked status only, what happens with linked status is if a cable is plugged into the switch, it's going to detect that that particular port is up. So as a result, it thinks that there's connectivity. If a network cable is unplugged, it's going to see that there isn't any network connectivity, and it's going to report a failure. It's going to report, there's a problem here, initiate failover. So that's the link status. As long as there's link, then it's up for it. As long as there's no link, so it's no green light, it's going to detect a failure. Now, what beacon probing does is it takes that one step further. It will still use link status, so it'll still try to detect if the port is up or down. However, what it'll do is it's a little smarter. So it'll send a message. It'll continuously send a message to that particular interface, so to speak. And if it doesn't receive a message back, like a heartbeat, if it doesn't receive an acknowledgement, then it's going to determine that there's a failure, and as a result, it will initiate a failover. So I'm going to leave this at default, and let's talk about notify switches. Now, by default, notify switches is set to yes. You can obviously set it to no if you choose to do so. Now, what notify switches does, it's a really cool function or feature. Anything that happens on the virtual switch, it automatically and immediately notifies the physical switches. So, for example, if you add another physical NIC to the virtual switch, then that virtual switch is going to notify the physical switches that, hey, I just added another uplink. You need to update your routing tables to acknowledge that there's a new physical NIC here, and that you can use it so that it can avoid latency. Otherwise, if you're adding another physical uplink and notify switches isn't there, then it's going to take time for the MAC address tables to be updated, etc. It might provide latency, maybe drop packets, etc., etc. So you always want to set notify switches to yes, so that if there's a failure and the virtual switch is able to notify the physical switch that, hey, I have a failure on one of the NICs, stop routing traffic to it, start routing traffic to the other physical NICs that are available based on the address tables that you have. So notify switches is very, very important. Now let's shift our attention to failback. Now again, the options are yes or no. And failback detects what's going on down here in this little box. So let me move one of these network adapters into a standby mode. So what happens when it's in a standby mode, all the traffic is always going through this particular physical NIC. In the event that this physical NIC fails, the standby is going to kick in, and it's going to become the active adapter, and that active adapter is going to now route traffic, right? Now, what the failback policy is asking is, hey, what do you want to do in the event that the original failed physical NIC has now been restored to active duty? Do you want it to sit in standby mode, or do you want it to become the active adapter and as a result kick the active adapter back into standby mode, or do you just want it to sit in standby mode and wait for another failure to happen and then it can go back into active mode? So in my opinion, if you're asking me, I would set this to no, actually, because if a failback has happened and the standby has kicked in and it's now working, well, what's the real reason? What's the hurry? What's the rush of putting the original one back into active duty? Keep the original one into standby mode, and if another failure should happen, then the failback just kicks in and it keeps going round and round and round, doing this particular thing. So I don't understand why it needs to fail back, but if there is any particular business case or a technical case, for that matter, that dictates that the original one has to go back into active duty and kick the standby back into standby, then you can set this policy to yes. So I'm going to go ahead and click on OK here. And let's go ahead and close. And that's all there is to it from a virtual networking perspective, folks. So what I'm going to do now is we're going to switch back to our presentation and we're going to recap what we've learned. This was a pretty cool lesson, huh? All right, so we started off by talking about virtual networking. We defined virtual networking, what does it mean, and talked about the fact that it's a logical entity within ESXi that you create to allow virtual machines to attach to it and then give them access to the rest of the physical network that's out there. I talked about network adapters, the physical network adapters, and I went into the vSphere client and I showed you where in the vSphere client on each ESX host you can find the network adapters and different views that you can see. You can see the auto negotiate, what they're connected to, the observed IPs for the different VLANs that they're connected to. We talked about virtual standard switches and what those means. What type of virtual standard switches are there? How many types you can create? We talked about the differences. So you can create an internal only one, you can create a NIC teaming one, etc., etc. We talked about the virtual standard switches functionality. We talked about the similarities between physical switches and virtual standard switches, what they share in common. We also discussed the differences between physical switches and virtual switches. We then talked about the types of virtual switches that there are out there. We moved on to the virtual switch ports. We discussed the fact that you have virtual machine port group, which means it's used to route virtual machine traffic, and you also have the VM kernel port group, and that's usually used for like vMotion, fault tolerance, the management network. And we talked about the fact that a VM kernel port group always requires the IP stack, so you always need to give it an IP configuration. We talked about a VLAN. What is a VLAN? It is a logical grouping, so to speak. It creates a logical virtual area network so that you can group certain types of traffic, certain virtual machines in that particular VLAN. We talked about how you can detect MAC address changes and forge transmits and make sure that those aren't altered if you're in a high security environment and you didn't want, for example, to allow vMotion to happen. Maybe you can set those to reject so that you don't allow that particular function from taking place. Finally, I hope this lesson was informative for you, and I'd like to thank you for viewing.